Okay, so today we are going to learn a very powerful technique, which is known as calculus of variations. Before we start, let me ask you this. Let's say in the three-dimensional space, you are given 2 points, point A and point B. So what is the shortest distance between these 2 points? Is it found by this curve, or this curve? Is it by psi 1, psi 2, or psi 3? It is psi 2, right? I believe you. But how will you convince an alien who has no idea about the physics of this world and he's only equipped with this calculus of variations knowledge? Okay, so let's see what we can do. Right. For all purposes, first of all, as I'm given only 2 points in the 3D space, I can consider it as a 2D problem, right? As any 2 points lie on the same plane. So effectively, let's take this as x and this as y. I'm left with finding the shortest distance between 2 points in 2 dimensions, right? I want to find this. What is this? Correct. Now let us take the actual solution as y of x, right? And the test case, some random function to be y tilde of x. Correct. So this y tilde of x is nothing but the solution curve in the neighborhood of y of x. And hence I can write y tilde of x is nothing but y of x plus epsilon eta x, right? This epsilon is the infinitesimal parameter, and this is a random function, right? So by varying this epsilon, I will get many like infinite number of curves in the vicinity of y of x, correct? Now I know from calculus that the distance between any 2 points can be found out using integral under root dx square plus dy square, correct? I can also write it as integration from xa to xb 1 plus dy by dx whole square. Correct. Now let us call this part as a function of y prime and x. Right. In variational calculus, we call this f as a functional, which is nothing but a fancy term for a function of functions. Right. So now I am left with I have L, which is a function of y and x, is nothing but xa to xb 1 plus y prime square under root dx. Okay. So now let us substitute y prime of x instead of y of x, because I'm interested in knowing what is the behavior of this functional in the vicinity of y of x, which is the actual solution. Right. So let us call that L tilde, which is nothing but xa to xb 1 plus y of x plus whole square under root. Right. Now what I want to do is, first of all, I'll expand this L tilde about epsilon equals to 0, right? Because by varying this epsilon, we are getting a family of different curves. Right. So I'm interested in knowing how that family of different curves impacts the value of this L tilde. Okay, so let us expand it using the Taylor series expansion. So I can write L tilde is nothing but L tilde at epsilon equals to 0 plus epsilon dl tilde upon d epsilon at epsilon equals to 0 plus epsilon square by 2 d square L tilde upon d epsilon, the second derivative at epsilon equals to 0 plus the higher order terms. Now let us recall from basic calculus. Okay, before that, I want you to think of an abstract space of functions. Okay. Take this as some space of functions. Okay. So now this space of functions are variables in our equation. Correct. So let's take for y equal to sine x, we get some value of L tilde. Right. We are getting some value. For y equals to arc tan x, let's take we get another value. So now corresponding to this functions y, the functional L will take several values, right? And we'll get a curve something like this. Okay. So now do you guys agree that the task of finding the shortest distance between these 2 points, A and B, right, is nothing but finding a function which minimizes this L curve. Right. Basically, we are interested in finding this point. what is this point? Correct. So from basic calculus, let us expand a function of single variable about point x equal to a. So now, if x equals to a is a minimum, how do I ensure that? Right. I should set x minus a f dash a equal to 0, right? We know this from our basic calculus. Similarly, if you see the Taylor expansion of L tilde, I have to set epsilon dl tilde upon d epsilon evaluated at epsilon equal to 0 to be 0, right? So let's do that. Let us evaluate dl tilde upon d epsilon. It's nothing but d of d epsilon xa xb 1 plus y prime of x epsilon eta prime of x squared x, right? As nothing is dependent on epsilon and epsilon is a free or independent variable, I can take this inside because these limits xa and xb are independent of epsilon. Okay. If I differentiate it, I get integral xa to xb 1 upon 1 plus y prime x plus epsilon eta prime x whole square and y prime plus epsilon eta prime of x into eta prime of x dx. Right? So now let us set epsilon dl tilde d epsilon evaluated at epsilon equal to 0 to be 0. Right? What do we get? We get xa xb y prime of x upon 1 plus y prime of x squared into epsilon eta prime of x dx equals to 0. Right. Now, if you remember in the beginning, what was epsilon into eta prime of x? It was nothing but y tilde of x minus y of x. Correct. And this thing is known as the del of y, which is nothing but first variation y. So let us spend some time on this del y term. What is this del y? So if you remember my original graph, if we had these 2 points, right, and this was the actual curve, right, y of x, and some arbitrary curve, I called it as y tilde of x. Correct. So what is del y? It is nothing but for a particular x, the difference between the varied solution versus the actual solution. So it means this one, these distances, right? Let's say this is for an x1, this is for an x2. Right. So if we go back to our original integral, we had xa to xb y prime 1 plus y prime squared under root del y dx equals to 0. Correct. Now I want to set this integral to be 0. Correct. So now do you guys agree that this del y, it can take any value, right? As we saw between these 2 points, at some points it can take a value of 0, at some points it will be positive, at some points it will be negative. Right? So how do I ensure that I set the whole integral to be 0? The only way is that I set this term to 0. Right? Now since y prime squared is positive, right, I get equation y prime equal to 0, which is nothing but the equation of a straight line. Right? Pretty cool, right? Isn't this a powerful technique? Right? So using this technique, we can find the solution to any problem. Right? Calculus of variation is a very powerful technique. So as long as you give me a functional, I will take the first variation of that functional, I will set that to 0, and I'll find the governing equation. Correct? The governing equations which we get after we set the first variation to be 0, they are known as the Euler-Lagrange equations. Right? So let's say you woke up in the future, right, and you are suddenly able to figure out a functional for, let's say, harvesting infinite energy or for time travel. Right? Just take the first variation of that functional to be 0, and boom, you can harvest now infinite energy, or you can basically time travel, right? So what we did today is for a very basic case for a 2D, but we can extend it to the higher dimensions. But remember, the heart of the technique will be the same. Take the first variation of the functional to be 0 and get the governing equations. Thank you.